This is a lesson on 2.3, calculating limits using the limit laws. Okay, our objective is for you to be able to understand and implement the limit laws of calculus in multiple cases, and we'll talk about what that is. And on your notes, this should be there. So basically, given that we have a limit, these two limits that exists, right, and c is a constant, we say that the limit of the sum is the sum of the limits. Okay, you might want to copy that down here, guys. And then for number 2, the difference of the limits, okay, the limit of the difference is the difference of the limits. Check. And then when we have limit of the constant times the function, you can pull that out and say constant times the limit of the function. In this case, the limit of the product of the function is the product of the two different functions. And the same thing goes with the quotient, or division, except the denominator cannot be 0. Sorry, that got cut off. X goes to approaches a. Okay, so these are the things that how you would say it verbally. Okay, let's try some here. Okay, all right. We're going to be using limit laws. So what we should do is we should have a sense of what we want to do. This one is approaching -2, so let me use this color, light blue, at x equal to -2. Now it's a limit, so in this particular case we have a limit as x goes to -2 of f of x plus 5 times the limit of x goes to -2 of g of x. So when you're looking at the f, the -2 is approaching this way, both of them. So that is 1, isn't it? And then for g, there's no whole nothing. That's just -1. No, hold on. It's -2. I got -1. Am I not seeing this correctly? Yeah, it is -1. Okay. So when you do that, that is 1 plus 5 times the -1, and that gives you -4. But I want you to put extra step over here, guys, just because we're just starting out. Okay. So that is equal to what? That is equal to f of in this particular case, I just want you to differentiate that. We have this over here. That is actually still the limit, right? But this one is 5 times g of -2. And g of -2 just happens to be equal to -1. The implication is that as long as the value here exists, right, you could just do a substitution. Okay? All right, sorry for losing my thought right there. Let me make it a little smaller so it'll fit in a little better. All right, let's choose different color. Okay, let's go with green. And we are going to the 1, so that is like right here, isn't it? X is 1. So in that case, we have a limit of x goes to 1, f of x, according to the limit law, times the limit of x goes to 1 of g of x. And that is equal to, at that point, f, the value exists, so that is equal to just f of 1 substitution, right? Times, and that particular value is what? Hold on. So we know that the limit as x goes to 1 is equal to that, right? So that's fine. But we have a little bit of the issue right now, right? Which is that the limit as x goes to 1 from the positive side of the g of x is equal to -1, which is not the same as the limit as x goes to 1 from the negative side, which is equal to -2, right? Let's put that over here. So because of that, limit of g of x is dne. Therefore, the limit, you should always go back to the original equation because that was the question, right? We're just providing the justification for all that. And when you multiply something like dne, or even add, subtract, or whatever, the whole thing doesn't exist, right? All right, make that a little smaller, and that should fit. All right, good. All right, let's go with, okay, magenta. So that's going towards 2, so which should be right here, right? So values here and here. So, but what we notice is this, the limit as x goes to 2 of f of x is equal to f of 2, which is approximately 1.4, isn't it? But what we notice is that g of x as x goes to 0 does not exist because the limit as x goes to 2 from the left, I'm sorry, that's not it. Sorry, my bad. I was looking at something else. Sorry about that. Is equal to 0. And you know that you cannot have a 0 in the denominator, right? So therefore, the limit as x goes to 2 of f of x over g of x simply doesn't exist. Okay? We'll just leave it at that. Okay? We'll leave that investigation at that point. If you want to actually go further into this, it's actually different. The reason is because the left limit and the right limit is different. If you think about it, it is going to a 0, right? It's not just that it's just undefined, is that it's going, this is positive 0. So if you divide by 1.4 by value that's like really, really small value that's going to a 0, but it's positive, on this side will be positive infinity. But on this side, because it's negative, it will be negative infinity. Right, so when you graph this thing, it will probably go this way and this way. Okay, but you don't need to go there. Just saying that g of x, the denominator being equal to 0, is sufficient to say the entire limit is dne. Okay, all right, guys. So let's slide over to the next page. Okay, so we have an additional law over here, guys, that we have to deal with. So basically, if you have something like this doesn't look right. Oh, I see. Okay, so the limit of that, right, some function to the power of n, is you could do limit of the function and then raise to the power of n on the outside. So this is actually an extension of a multiplication limits, right? So no matter what happens to a, whatever it's approaching, if it's a constant, it's constant, right? So for this, the example might be this. So no matter where along the x-axis you are, my y value doesn't change. And this one is just y equal to x, right? So that implies that function y equal to x, so equation y equal to x. So whatever the x value is, if it's a, my y value has to be the same. That's essentially what it's saying. And this is an extension of that in a similar way that this is this was an extension of the product rule. And then if you could do a power, you could do it to the radical, because if you think about it, the radical is a form of power, because this is equal to a to the 1 over n, right? And this, by extension, is same as that, because once again, radical is a form of an exponent. Okay. And we already learned earlier that as long as when you do a direct substitution and it doesn't create any kind of weirdness, like 0 over 0, right? You could do a direct substitution. And one of the rules is that when you have a polynomial like this, you should be thinking direct substitution. So you have express permission to do that. So that is equal to twice the 5 squared minus 3 times 5 plus 4. That's a 50 minus 15 plus 4 minus 11. So that must be 39. In this particular case, you got to be wary because we have actually what? A quotient. So when I plug this value in, which is -2, into this, let me just switch a little bit more, right? Do you get a 0? Actually, we don't. So if that's the case, once again, you could do a direct substitution. So that's -2 cubed plus 2 -2 squared minus 1 over 5 times 5 minus -3 times -2. That is -8. That is plus 8 minus 1. So the numerator is -1. So that is 5 plus 6, -11. Okay. All right, guys. Now we do slightly something more interesting. What I said earlier, right? You could do a direct substitution if it's a polynomial, a rational function, and then whatever you put in doesn't give you any weirdness, right? So that was from the previous. This one is a little bit different, so I perhaps should have put it up there. Sorry about that. We're going to do a indeterminate form of 0 over 0. When I plug in 1 into this, I get 0 over 0. In those cases, the things that you could do is you could try to put it in different form. And in this particular case, we should factor. And we know that x minus 1's cancel, and that is x plus 1 as x goes to 1. Now has become a polynomial. You could do direct substitution, which gives you 2. You might have a question over here. What just happened over there, right? Can you really do that? What kind of sorcery is this? So we have a question. So let's make a note about it. So when you have x squared minus 1 of x minus 1, we know that it is x plus 1 as long as where x cannot be 1. But here's the thing though. So these two are not equal to each other. But these two are equal to each other if you have this particular statement. Without this, they're not the same. With this is good. But I don't have that statement over here. Why are they equal? Well, that is because the limit expression says it is approaching 1. Implies that it is not equal to 1. Because the x will never be 1 because it's approaching, you don't need this statement. So these two are actually equal statement as long as we have this expression x is approaching 1. The implication is it is not equal to 1. That is why you're allowed to do this. Sounds good, guys? All right. So we have this over here. Let's expand it out. And when you do, that's 9 plus 6h plus h squared minus 9 over h. You know, this cancels, right? And then we could sort of factor out the 6 in the numerator. That should be h. I'm sorry about that. h. And h over 6 minus h over h. They cancel. So now it's the limit as h goes to 0 of 6 plus h. Now I could plug in for h directly, which yields 6 plus 0. Therefore, the limit is 6. Right? We have a few more problems to do, but let's sort of wait for that in the classroom situation. So we'll have something to talk about. Okay? But I want you to sort of think about it. Here's my hint for this case, guys. Think about the graphic form. Think about the graphic form, or when you see absolute value, what should you do? There are a couple ways to approach it, but in terms of a function, you should be thinking about piecewise function. In this case, absolute value, same thing. All right, guys, that is something to think about. So I shall see you in class. Thank you.